The manufacturing of aerospace composites is both highly complex and relatively simple. It's true that many precise steps must be followed in each of several processes to create a reliable, attractive, and properly performing part. But you should also know that each individual step can be pretty easily accomplished with average skills, a basic understanding of math, consistent attention to detail, and a lot of good old-fashioned practice. We're going to take a look at these many procedures, steps, and processes and see if we can't take some of the mystery out of the apparently overwhelming job of making parts that fly. We'll get a preview of the various tools and materials we'll be using, and process by process, we'll follow a part as it's fabricated and finished. From the preparation of the mold to the layup of the layers of composite material, the bagging of the raw part, curing in an autoclave, removing the part from its bag and mold, trimming, sanding, drilling, and assembly of a high-quality composite part. It may be on actual paper, a chalkboard, or a monitor, but every modern industrial process has it: paperwork. This documentation may be a single work order, or many pages or screens of highly detailed information and instructions. In aerospace composite manufacturing, checking and following this documentation is critical. It's a ready reference that identifies the part to be built and the tooling and materials to use, as well as complete part and process specifications. There are also additional documents to log temperature-sensitive materials in and out of cold storage. The process specifications have been developed through exhaustive research, design, and testing. They are not suggestions. They are requirements. All work must be performed IAW in accordance with these process specifications. Most aerospace composites use textile reinforcement. These fibers or yarns are either unidirectional, where the fibers run in only one direction, or they're made into a woven bidirectional fabric. The yarns that run the length of the woven fabric are called the warp, and the perpendicular yarns that run across the warp are called the weft or fill. The side edges of the material are degraded by the mechanical stresses of weaving and are only used for handling and marking. This area is called the selvage. To streamline the production process, we'll be working with a special product that combines this textile reinforcement with uncured resin. It's a resin-impregnated fabric called prepreg. Carbon fiber prepreg is used for its strength and low weight, but wherever the part is going to be in direct contact with aluminum or exposed to damaging stresses, a fiberglass ply is added as a protective corrosion layer. All prepreg has a limited shelf life. Even when it's bagged, sealed, and frozen, the resin will slowly cure, so it's only good for about a year. Once it's thawed, the resin cure accelerates. Because of that, all prepreg must be logged out when it leaves the freezer and logged back in when it's returned. This out time must be tracked so we can tell when the product is expired. Production parts may never be made with expired material. Another characteristic of the woven prepreg that must be documented is the orientation of the weave. In assembling a composite, layers or plies of prepreg are stacked on a mold. The way the fibers of each ply run within the composite is important. They help determine many physical properties of the part. For example, a part can be engineered stiff to resist movement, or it can be designed to flex to absorb energy. As we work with prepreg, we track ply orientation using the warp of the fabric. A line running with the warp is our zero reference on what's called the warp clock. If we rotate the prepreg 1/8 turn counterclockwise, the warp is sitting at plus 45 degrees relative to the original zero warp. If instead we rotate the prepreg 1/8 turn clockwise from zero, the warp is at minus 45 degrees. If we rotate a full quarter turn from zero in either direction, that's 90 degrees. The warp clock works like a compass, reminding us how to position the warp fibers as we cut prepreg for a part, and then later as we stack the plies on the mold in layup. If the prepreg is cut using a template, the rotation of the template is the reverse of rotating the prepreg itself. In other words, if we rotate the template counterclockwise to plus 45 degrees, the prepreg cut at this orientation will have its warp at minus 45 degrees. The orientation specified in the work instructions will always be warp orientation, never template orientation. As each ply is cut, a special silver marker is used on the prepreg to identify the specified warp position, which would be either 0 degrees, minus 45, plus 45, or 90 degrees, and the original zero warp reference, the direction the warp would have run if the ply had been cut at zero warp. We call this mold zero. Then, during layup, the zero mark on the prepreg is simply matched to the zero mark on the warp clock that's found on every mold. As the production process begins, the documentation is checked for the number of mold to use, the types of prepreg required, the number of plies of each type needed to build the part, and the orientation of each ply. The bolts of prepreg can then be removed from the freezer, the time noted on the outtime log, and the prepreg set aside to defrost. When the prepreg has reached room temperature, it's ready to be cut. After the part pattern is matched to the mold and part, the pattern is laid or laser projected onto the prepreg and rotated to the proper orientation. Once the pattern is traced onto the prepreg, the ply is marked with a warp orientation and mold zero, and then the prepreg is cut to create the first ply. After rotating the pattern, then marking and cutting each additional ply, the unused prepreg is returned to the freezer, and the time is recorded on the outtime log. The molds that are used to create aerospace parts run from small and simple to large and complex. Basically, they're forms that have the exact contours of one side of the part to be produced. With only a few exceptions, these molds, often called tools, are larger than the part. A mold border is needed beyond the finished part profile to allow for trim area on the part and to provide an attachment area for the various films, ports, and sensors used in the vacuum bagging and curing processes. Before a mold can be used to lay up a part, it must be inspected, tested, and prepped. This includes a visual examination, a mold integrity check, cleaning, sealing, and the application of a release agent. Once the mold has been matched to the work order and moved to the production area, it must be carefully inspected for damage, such as dents, cracks, or significant scratches. If the mold appears good, it still must be tested for vacuum leaks. To run a mold integrity check, we'll need the mold cleaning solution, lint-free mold cleaning wipes, tacky sealant tape, a breather layer, which is a thick, air-permeable felt-like material, 2 vacuum ports and their locking port bases, and bagging film. The steps in the mold integrity check are very similar to debulking and layup and final bagging. In each process, we seal, bag, and draw a vacuum. First, the mold border must be thoroughly cleaned with mold cleaning solution and lint-free wipes. All mold cleaning must be done with the double wipe method. One hand wipes with a wet cloth, then the other immediately follows with a dry wipe. This ensures that the solvent doesn't air dry on the mold surface. When the mold is clean, tacky sealant tape, also called mud tape, is applied around the border, staying well outside the part layup area. The paper backing must be left on the top of the tacky sealant tape. Next, a piece of breather layer is cut to fit inside the tacky tape outline. The breather is placed within and not touching the tape. 2 additional 3x3-inch squares of breather are cut, positioned on top of the breather layer on opposite sides of the mold, and flash taped in place. The vacuum port bases are now put on top of the squares. This extra thickness of permeable material will ensure that air can still be drawn through the port, even when vacuum has compressed the breather layer. Now we're ready for the bagging film. The film is carefully placed over the mold, cut to size so that it overlaps the tacky tape by at least a couple of inches, positioned over the mold, then folded back away from the operator. The backer is removed from the tacky tape near the operator, and the bagging film is pulled back over and down onto the tape, while the film is lightly tensioned between the operator's hands. Next, the loose film is folded back toward the operator, exposing the remaining protected tacky tape. The rest of the paper backing is removed, and the bagging film is lightly tensioned as it's lowered onto the exposed tacky tape and conformed to the mold. The tacky tape seal must be closely examined to make sure that the bagging film is in full contact with no gaps. If the seal looks good, the film can be pressed firmly into the tape. The vacuum ports can now be attached to their bases. First, any wrinkles or folds in the bagging film over the port bases are smoothed out, and a small X is cut in the film directly over each base. Then the port is centered over the base and pressed down and twisted to create an airtight seal. Now the vacuum line is attached to one port, a vacuum gauge to the other, and a vacuum, about 25 Hg or inches of mercury, is pulled to check the mold for leaks. The vacuum is then disconnected and the gauge is monitored. If the vacuum doesn't fall below 20 Hg within 5 minutes, the mold passes the test and we can continue with prep. Next, the mold is stripped and all test materials are properly discarded. Then the entire mold is cleaned using the same solvent, lint-free wipes, and double wipe method. The clean mold can now be taped off. Flash tape is used to protect a path for the tacky tape that will come later. The tape is run within the border of the mold, away from the part layup area. Next, mold sealer is applied, inside the tape only. The work instructions may call for up to 4 coats of sealer, with oven curing after the final coat. The mold sealer fills in any tiny irregularities in the mold surface, ensuring that the finished part will be as smooth as possible. After the sealer dries, the work instructions may require 2 coats of a release agent, again only inside the tape. This coating will prevent the part from sticking to the mold. The first coat is applied all in one direction, while the second coat is applied at a 90-degree angle to the first. For instance, side to side with the first, then top to bottom with the second. When the release agent has dried, the flash tape is removed, and this mold is ready for layup. In layup, layers of material are carefully stacked on the mold, in the precise order detailed on the work order. The mold is already tested and prepped, and a release agent has been applied to the layup area. We'll be putting down tacky tape, orienting, stacking, and smoothing the various plies of prepreg, covering the prepreg with release film, and a breather layer, installing temperature sensors called thermocouples, covering the part with bagging film, attaching vacuum ports to the bag, and drawing a vacuum on the bagged part. When we finish this process, the part will be ready for curing. Layup begins with checking the documentation and making sure that we have the right mold, pre-cut prepreg, and layup supplies. First, tacky tape is run around the entire mold border. Although a liquid release film is often applied to the mold during mold prep, some parts may specify a separate solid release film instead. And sometimes a special surface film called a sanding layer will be required. Both films must be cut to fit well inside the tacky tape border. The first ply of prepreg can now be stripped of its backing and positioned over the mold, lined up, ply 0 mark to mold 0 mark, laid against the mold, and smoothed to remove any folds or wrinkles. It's best to start smoothing at one edge and work across the ply. Smoothing can be done by hand, using a pusher, or with a small roller. Where the ply crosses an inset, inside corner, or other concave feature of the mold, extra care must be taken to push the ply fully into the feature so that it's flush with the mold or the ply directly underneath. If the prepreg lifts off the mold, or if a gap forms between plies, it creates what's known as bridging, weakening the part and requiring it to be scrapped. After the first ply is fully conformed and wrinkle-free, additional plies are added one at a time. Each one is positioned as documented relative to the zero warp reference, laid directly on top of the previous ply, and smoothed out, working from edge to edge. Thicker parts will often have to be debulked during the layup process. It may even be required for the first ply, but the industry standard is to debulk after every fourth ply. This step is fairly similar to the vacuum test we did during mold prep. When the work order calls for debulking, a layer of release film is placed over the part and flash taped at the edges. A breather layer is added and taped. Additional 3 by 3 inch squares of breather material, one for each vacuum port, are placed on the edge of the breather layer away from the part and taped down. A vacuum port base is placed on each square. A piece of bagging film is cut and placed over the mold. The paper backing is removed from the tacky tape. The bagging film is lightly tensioned across the mold and pressed into the tacky tape. Then a small X cut is made directly over each vacuum port base, and the vacuum ports are pressed down onto the bases and twisted to seal. As a vacuum is drawn to compress the plies of prepreg, any wrinkles or folds in the bag must be worked to the edges of the mold off of the part. When the plies are fully compressed, the vacuum hose can be removed, and the bagging film, breather, vacuum port, release film, and tacky tape removed. New tacky tape can now be applied, and the next set of prepreg plies positioned, oriented, placed, and smoothed. When the last debulking has been done and the last ply has been placed and smoothed, we're ready to prepare for final bagging. First, thermocouples are placed, per the work instructions, usually on the waist edges of the part, and secured with flash tape. A small section of the paper backer is removed from the tacky tape where the lead crosses. A new small piece of tacky tape is placed over the lead, and the leads inside and outside of the tacky tape are secured to the mold with flash tape. Then we can finish the layup with release film, a breather layer, extra breather material for the vacuum port bases, and the bases themselves. Now it's time for final bagging. For simple, relatively flat parts, the bagging film is usually close-fitting, but for more complex parts, extra film surface is needed so the bagging can fully conform to the part contours and to prevent bridging. In either case, the bagging film is laid over the part and folded back on itself. The paper backer on part of the tacky tape around the mold is removed, and the film is folded back across and laid on the tacky tape. Now, section by section, the rest of the paper backer is removed, and the unsecured bagging film is pulled back across the part and laid on the exposed tape. Any excess film is either pulled off the part surface or pleated. These pleats are special fold patterns that enable the film to draw down tightly against the part while controlling the placement of any excess film. These pleats are also used along the edge of the bag, where extra loops of tacky tape rise from the perimeter seal to create an airtight film-to-film bond. After the tape seal is checked for voids and wrinkles, the bagging film is pressed fully into the tape, and then any excess film is trimmed off the edges. Now small X's are cut into the bagging over the center of the vacuum port bases. The ports are positioned over the bases, and then pressed down and twisted to lock and seal them. The bag is now smoothed over the part surface, and a vacuum line and gauge are connected to the vacuum ports. As the bag draws down against the part, any remaining folds or wrinkles must either be moved off the part surface or pleated to allow maximum consistent pressure against the part. This bag part is now ready for curing. In curing, a vacuum bag part is exposed to heat and pressure, The heat lets the resin in the prepreg flow while speeding up the curing process. The pressure pushes the plies of the part together, pressing them down against the mold. All the variables in curing, time, temperature, atmospheric pressure, and vacuum, must be tightly controlled to create a quality part. To give us this control, a programmable autoclave is used to manage the curing process. Curing has 3 stages: ramp up, dwell, and ramp down. To prepare for curing, the parts, bagged and under vacuum, are placed in the autoclave. One vacuum port is connected to the autoclave vacuum system, while the other vacuum port is connected to a vacuum monitoring system. The part's thermocouple leads are connected and checked, and then the autoclave is closed and sealed. The process begins with ramp up. During ramp up, the pressure and temperature gradually rise. As the pressure inside the autoclave increases, the vacuum on the part decreases. Volatile gases generated by the curing resin, along with trapped air and moisture, start to bleed off the part. Then, during dwell, the part is held at an ideal temperature to cure the resin. In curing, the components of the resin cross-link, forming highly durable molecular bonds. Finally, during ramp down, the part is permitted to cool while the autoclave pressure is gradually vented. As soon as the cured parts have cooled enough to be comfortably handled, they're ready for debagging and demolding. Before the cured part can be removed from its bag and mold, it must be disconnected from the autoclave systems. That includes all hoses on the vacuum ports and the leads to the thermocouples. The part can now be moved from the autoclave to the debagging and demolding area. The first step in debagging is to remove the vacuum ports. Each port must be twisted counterclockwise to free it from the port base, and then set aside for reuse. Now the bag itself can be removed. Starting at one corner of the bag, it's pulled up and over the part. Special care must be taken to prevent damage to the thermocouple leads as the tacky tape seal is removed. After the vacuum port bases are salvaged, the layers of material on top of the part can be stripped off and discarded. That includes the breather and release film. Then the thermocouples are removed and saved for reuse. Now the part can be demolded, removed from the mold. For product and operator safety, gloves must be worn as the part is handled. If the part sticks to the mold, nylon pushers can be used to help pry it loose. The new part can now be carefully examined, and any defects or blemishes reported. Before the mold can be returned to storage or reused, all traces of resin, tape residue, and release agents must be removed using an approved mold cleaning solution. Debagging and demolding are complete. The cured, inspected part is ready for the first finishing operation, trimming. Several operations are used to finish a rough part: trimming, sanding, drilling, and final assembly. Trimming, the first step, begins with marking the part. Every part must have 2 trim lines: the NTL, the net trim line, and an RCL, or rough cut line. Cutting along the RCL will give the part its approximate shape, while sanding down to the NTL gives the part its final dimensions. Marking the part requires a special pencil or marker that's approved for use on carbon fiber composites and a rigid template that has the precise profile of the finished part. The template is registered to the rough part, and a line traced around the edge of the template gives us the net trim line. Next, we'll create the rough cut line by measuring and marking 3 millimeters out from the NTL in several spots along its length, and then drawing a line that runs through all those marks. Parts that don't have templates are either produced on molds that have net trim tooling marks, or they're measured and marked based on the engineering drawings. With the NTL and RCL marked, we're ready to trim. For the rough cut, we're using a die grinder with a diamond edge blade. Then the coarse sanding is done with a die grinder sander. And to get right down to the net trim line without crossing inside it, we rely on hand sanding. Now that the part is trimmed, we need to make sure that it's not defective or damaged. That means checking it for flaws such as delamination, that's where plies have separated, splintering, gouges, or excessive trimming that has crossed the NTL. Once this part has passed inspection, it's ready for surface and finish sanding. The goal of finish sanding is to create a part surface that's extremely smooth, one that not only looks good, it also offers very low resistance to air flowing across it. To create that aero-smooth surface, we have to use the right tool, the right abrasive, and the right sanding technique. The right tool is an orbital sander. This type sander, when used properly, doesn't leave a directional track. Hand sanding creates tiny scratches in whatever directions the abrasive is moved. Belt sanding leaves tracks in the direction of belt movement. And rotary disc sanders leave concentric circles. But orbital sanders vibrate the abrasive pad randomly, both up and down and around. The abrasive particles are only in intermittent contact with the part's surface, so no tracks. To prepare for sanding, the part should be placed on a protective, slip-resistant surface, or put in a jig to hold it steady. The right abrasive and grit should be specified in the process documentation. A 320 grit or finer is often used. Sanding should be done with smooth, even strokes. The sander should glide across the surface, always moving, with only a very light downward pressure. And the sander must never be tipped up to press on one edge. It should stay perfectly flat, with the abrasive pad parallel to the part's surface. If the part has a sanding layer, that entire layer must be gradually sanded off, leaving residual material only in small surface imperfections as a filler. The part's surface should be regularly checked during sanding, and carefully inspected after sanding for damage or flaws. Scratches or gouges might be repairable, but splintering, delamination, or exposed fiber will almost always result in expensive repairs or scrapping of the part. When sanding is complete and the part has passed inspection, it's ready to move on to the drilling operation. There's a lot more to drilling a composite part than you might think. Because drilling prepares parts for assembly, and assembly must be very precise, several critical steps are involved. After the process documentation is checked, the hole pattern for the part is carefully and precisely laid out. The parts to be assembled are aligned and marked. The proper drill bits, both size and type, are selected, and the pilot holes are drilled. Then the final holes are drilled and smoothed. Some holes are finished with a conventional countersink, or a partial countersink called a fillet, and temporary fasteners are installed. There's a lot to know about each step in the drilling process, and it all starts with the documentation. The process documentation must be checked for the specific parts to be joined, the type, size, and number of fasteners to be used, and a lot of information about the placement of the holes for the fasteners, including how far the fasteners are from the edges of the part, that's edge distance, or ED, how far the fasteners are from each other, called FS, for fastener spacing, and how far the rows of fasteners are from each other. That's known as RS, for row spacing. The documentation also shows us the individual tolerances for ED, FS, and RS. That's how far off position each can be without ruining the part. With this information in hand, we're ready to align and mark the components that make up our assembly. These components may be composites, or a mix of composites and metal. One of the documents, an engineering drawing, shows us how the components fit together. After they're aligned and double-checked, it's time to index mark each component for proper orientation. A special carbon fiber-approved pencil or marker is used for composites, and a designated soft-tip marker for metal. The same markers can now be used to lay out the hole pattern. Following the specifications in the documentation, we measure and mark the edge distance along one edge of the part. then along the opposite side. Then mark the edge distance in from the remaining sides on the ends of those lines. This edge distance is measured from the center of each fastener, so each hole will be centered on the ED line. Now we can calculate exact fastener placement. Keep in mind that any line that has equally spaced points from end to end will have one less space than it has points. For instance, 10 points means 9 spaces in between the points. The drawing shows us how many fasteners to use on a particular ED line. All we have to do is measure our usable line length, that's from ED intersection to ED intersection, and divide that length by the number of fasteners minus 1. If we have 10 fasteners, we divide by 9. That gives us our FS, fastener spacing. The first fastener and drill mark is at the ED intersection at one end of the first ED line. Now, measuring from our original reference, the part edge, ED plus FS gives us the second mark. Plus FS again gives us the third, and so on. By keeping the rule in fixed position, we can be certain that each measurement is exact. Moving the rule would cause tiny errors with each shift, an effect known as tolerance buildup. Once all fastener center points have been marked and checked, we're ready to select our drill bits. The bits must be compatible with all the materials in the stack-up. Drilling puts a lot of stress on composites. The wrong type bit or the wrong speed or even the wrong feed rate can cause splintering, chipping, delamination, or overheating. It can even melt the resin. If the work instructions don't specify what type of bit to use, the operator will have to choose based on the materials in the part. Most conventional composite or composite and metal assemblies will require either carbide or PCD bits, that's polycrystalline diamond. Non-metallic carbon fiber assemblies may call for long helix left-hand drill reamers. To ensure minimal strain on the composite material, we must also use the right size bits. A hole for a typical small fastener might require 2 or 3 bits, one to start the hole and bore the pilot, and then 1 or 2 to gradually size the hole up to its rough finished diameter. The larger the rough finished hole, the more intermediate bits are needed. To make sure bits don't cause damage or injury as they exit the back side of a part, we often use a drill stop with a bushing. The stop is a collar that's attached to a bit at the target depth, and the bushing helps guide the bit while protecting the part from the spinning stop. If the bottom layer where the bit exits is composite, a drill backer is sometimes required to prevent delamination or splintering of the composite material. In a finished part, all the fasteners must lie flat on the composite surface. If a hole is accidentally drilled on an angle instead of straight, the head of the fastener can't lie flat. It will be tipped up on one edge, creating a poor mechanical joint and leading to fastener failure. To ensure that each hole is truly perpendicular to the composite surface, we regularly use drill cups. When a drill cup is fitted with a properly sized bushing, one that exactly matches the bit diameter, the cup serves as a drill guide, keeping the hole plumb and straight. A good hole begins with a good drill start. A drill start is the small dimple made with the tip of the bit that keeps the bit from skating off the mark as pressure is applied. To create a drill start, the bit is rotated until the tip is easily visible. And, with the bit held at a 45-degree angle to the part's surface, the tip of the bit is placed directly on the first hole center mark. Then the bit and motor are brought to a perpendicular position over the mark, and the drill chuck is rotated by hand to create a clean, well-positioned drill start. After all the drill starts are completed and checked, we're ready for the pilot holes. With a drill stop already installed on the bit, a drill cup with a right-sized bushing is slid over the bit and down to the stop. The tip of the bit is placed directly on the first hole drill start. With the bit and motor in a perpendicular position, the drill cup is slid down the bit and brought to rest evenly on the composite surface. Then, with the cup held firmly against the surface, the drill is started and the bit is slowly fed into the new hole and down to the stop. After all the holes have been drilled and sized to specifications, they're ready to be finished. The first step in finishing is deburring. Deburring creates what's called a net condition, a smooth part surface without splinters, burrs, or delamination. Holes in composites are deburred by hand using a fine grit abrasive paper or pad. A few twists of a finger or thumb directly over the hole are usually enough. Deburring holes in metal requires a countersink cutter with a microstop cage. The countersink actually bevels the top edge of the hole, while the stop ensures that the cut isn't too deep. For flush fasteners, a traditional countersink cut will let the head of the fastener sit down in the part, level with the surface. A countersink is also used in another hole finishing step for metal components that's called fillet relief. Many fasteners have curved or ramped shoulders where the head of the pin transitions to the shank. This part of the pin is called the fillet. By cutting the top edge of the hole back with a countersink, we create room for the fillet to seat in the hole, and that means the head of the fastener can lie flat against the part surface. This creates a more aerodynamic part surface and a better mechanical joint while relieving stress on the composite directly around the fillet. Drilling stack-ups requires a few specialized steps. All of the components of a stack-up must be carefully aligned before drilling and firmly clamped together. Holes are drilled in a sequence that helps keep all components aligned. The first hole in the first row is drilled and rough finished. Then a properly sized cleco fastener is temporarily installed in the hole to keep the components aligned. Then the last hole in the last row, diagonally opposite the first, is drilled and finished, and a cleco is installed in that hole. Then the remaining corners can be drilled and fastened. The components are now locked in alignment, so the clamps can be removed and the remaining holes can be drilled and fastened with clecos in a regular sequence. Only one more step is needed to finish the holes for assembly: final drill and ream. Standard bits and drill cups are used to rough size each hole 8/1000ths of an inch smaller than its specified final size. A special reamer bit is then used to smooth and enlarge the hole to its precise finished diameter. When all the holes have been reamed to the proper size and spring lecos installed, the part is ready for final assembly. There are several steps involved in preparing and assembling a stack-up. There's disassembly, cleaning, inspection, applying sealant between components, aligning the components, installing draw clecos, squeezing out excess sealant, cleaning up excess sealant, installing permanent fasteners, another good cleaning, and applying a fillet seal. As the process begins, the spring clecos are removed from the stack-up and the components are cleaned with an approved solvent. Next, sealant is applied and spread to target thickness on all face surfaces. Face surfaces are the component faces that are in direct contact with other component faces in the assembly. All the components are then indexed and aligned, and the face surfaces mated. The pin of a draw cleco is used as a pilot to help align the components as they come into contact. Draw clecos are then inserted in every fourth hole, or on smaller assemblies, just in the end holes or corners. After all clecos are in place, they are tightened in the sequence and to the torque specified in the work instructions. The pressure generated as the clecos are tightened gradually draws the face surfaces into full contact and squeezes excess sealant out the edges of the joints. This squeeze-out is a sign of a good bond. After the edges of the face joints are cleaned of excess sealant, we're ready to begin installing permanent fasteners. There are several types of permanent fasteners that are used in aerospace manufacturing. Two of the most common are the high lock and the lock or huck bolt. These bolts are identified by their composition, that's the materials and coatings they're made of, the head type, protruding or countersunk, the diameter of the pin, that's the body of the bolt, and the grip length of the bolt, that's the thickness of material that the bolt is designed to bind. The high lock is a two-piece fastener, the pin, which has a head and a shank, and a threaded collar. The shank has a smooth shaft with a threaded end to receive the collar and a hex receiver in the threaded end to keep the body from rotating as the collar is tightened. In use, the head sits on or just flush with the outside surface of the part. The pin runs through the stack-up with only the threaded section protruding, and the collar threads onto the end of the shank. The hex section of the collar permits the collar to be rotated down the pin and into contact with the part. When the collar is rotated to maximum torque, the hex section breaks away, leaving a perfectly tensioned fastener. The lock or huck bolt is similar, except that the end of the shank has locking grooves instead of threads, and instead of a threaded collar, it uses a deformable collar, which is compressed around and into the locking grooves of the shank in a process called swaging. A special tool called a pull gun is used to properly tension the bolt, swage the collar, and snap off the end of the bolt. The final steps of assembly begin with the installation of permanent fasteners. The first open hole in the first row of fasteners is inspected for damage or foreign material and cleaned if necessary. The first permanent fastener is then installed, torqued or tensioned as specified in the work instructions, and inspected. The head of the fastener is checked to ensure that it's laying either flat or flush, while the collar end is checked with a go-no-go gauge for proper installation. The process continues following the fastener installation and replacement sequence specified in the work instructions. As soon as the stack-up is secure, any remaining clecos can be removed and replaced with permanent fasteners. All that's left is the fillet seal. The fillet seal protects the joints where one plate in a stack-up steps down to another. It forms both a durable seal and an effective ramp transition to improve airflow across the assembly. After checking the work instructions for the width of seal required, the seal area is thoroughly cleaned with an approved solvent and wiped dry. The seal area is then laid out, first with an approved pencil or marker, and then with masking tape, directly over and outboard of the marks. Once the seal area dimensions have been double-checked with an engineering rule, the specified sealant is applied directly into the base of the joint and smoothed out with a fairing tool. Then the seal is checked, the tape is removed, and the sealant along the tape border is re-smoothed if necessary. After the sealant has cured to tack-free, all marker or tape residue is removed with an approved solvent, and the part is wiped dry. In a few hours, when the fillet seal has fully cured, the part receives a final detailed inspection, and then it's ready for shipment or installation.